Hi, AP Chemistry. Welcome back to talking about acids and bases. We're going to talk about water a little bit. We've kind of ignored water and water's role in acid and base reactions, but I want to kind of revisit some reactions that we talked about yesterday and talk about the role of water. So you may have noticed that water was involved in both the acid reactions as well as one of the base reactions that we looked at. So let me write these out for you again, and we can take a closer look at water in both of these reactions. So HCl reacts with water. And so does ammonia. Okay, so if you look at these two reactions, you'll see that water's involved in both of these, but water plays a different role in both of these reactions. So go ahead and look at water. See if you can identify the role that it's playing. How is water's actions different in both of these equations? Okay, in the first equation with acid, water and chlorine are both fighting over a hydrogen. And that hydrogen starts attached to the acid. In the second equation, nitrogen and a hydroxide group are both fighting over a hydrogen. And the hydrogen initially is attached to the water. Excuse me. Okay, so notice that the hydrogen that's being fought over in both of these equations is attached to something different. In the first equation, it's attached to the acid. In the second equation, it's attached to the water. And what results is also different. In the first equation, if it moves forward, which it will because it's a strong acid meaning it dissociates completely. So strong acid meaning weak anion, right? In the first reaction, what results is a hydronium ion. And then when we get lazy, we write the hydronium ion as hydrogen. In the second equation, what results is a hydroxide ion. So slightly different battles going on with slightly different results. Now, before we go any farther, I want you to take a minute and see if you can decide if water is acting like an acid or a base in both of these equations. So hydrochloric acid, obviously an acid. Ammonia, obviously a base. But what's water? This would be a good time to pause the video, come up with a definite answer, and then come back to us and we'll talk about it together. So notice in the first equation, if water is successful in winning over this hydrogen, water is going to be the hydrogen acceptor, which makes it a base. In the second equation, if water changes, water is actually the hydrogen donor, which makes water an acid. So notice that water can act like a base in some circumstances. Water can also act like an acid in certain circumstances. We say that water is amphoteric. It has multiple ways that it can behave. Not everything can do this. Hydrochloric acid certainly can't. Hydrochloric acid is a hydrogen donor. It never acts like a hydrogen acceptor, right? It's not amphoteric, but water is. Water is in a very small group of compounds that can act like an acid or a base depending on the circumstance that it is in. It's an amphoteric compound. Another thing you might notice is that in a reaction, if you have an acid, you also have a base. And this is often true. If something is acting like a hydrogen donor, then something else is going to be acting like a hydrogen acceptor, right? Acids and bases often are found paired together like this. Actually, we can look at the products. We can also label the products as acids and bases as well. Why don't you pause the video here, take a minute, see if you can label those 4 products, 2 for the first reaction, 2 for the second reaction, as an acid or a base, depending on the definition that you're using. Okay, so in the second equation, if hydronium reacts with chlorine, okay, so notice we're looking at the reverse reaction. Hydronium would be acting like the acid donor. It's going to be an acid. Chlorine would be acting like the hydrogen acceptor. It's going to be the base. Likewise, ammonium and the chloride ion, the hydroxide ion act in similar ways. If these two were to react together and push the reaction in the reverse direction, ammonium would act like the hydrogen donor, making it the acid. Hydroxide would act like the hydrogen acceptor, making it the base. Okay, so notice we have labeled everything in here in these reactions as an acid or a base. Now, this is not as easy to do if you were to write the hydrochloric acid as a dissociation reaction. It's a lot harder to look at this dissociation reaction and label things as acids and bases, but you still can in some respects. This leads us to our conjugates. So notice that hydrochloric acid is an acid and it has a conjugate base, right? The anion of our acid is the acid's conjugate base. Water is a base and its conjugate acid is hydronium. Same thing on the second reaction. We have ammonia and its conjugate acid. We have water acting like an acid, and it's getting complicated. Hydroxide is its conjugate base. So notice, if you have an acid, you will have a conjugate base. If you have a base, you will have a conjugate acid. You should be able to look at reactions, label these things, and match up the things that are conjugates together. Okay, so now that we have this understanding that water can act like an acid or a base, I want to show you what water does when it's by itself. So water, when it's by itself, can actually react with another water molecule. So let me see if I can draw this. So water can react with another water. And these two things are going to be fighting over a hydrogen. So we have a hydroxide ion trying to hang on to that hydrogen. We have another water trying to battle for that hydrogen, right? So this reaction would look like two hydrogens, and if it goes forward, it would result in an H3O plus and an OH minus. Again, you can write this as a dissociation reaction, just as kind of a shorthand. It doesn't actually display what's going on, but it is a useful shorthand. Okay, so anyway, here is our reaction of when water reacts with water. And when water reacts with water, it forms ions. This is called the auto-ionization of water. This is the auto-ionization reaction of water. This actually happens in water, I want to say solutions of water, but that's not, it's kind of mislabeled, right? In bodies of water, water actually reacts with water, pulls itself apart and forms ions. Now, it doesn't do this to a great extent. Not very many collisions of water molecules with other water molecules end in a successful reaction. Most of the time, they just bounce off of each other, right? But sometimes they do collide with just the right amount of energy, the right orientation. The reaction actually happens. And when you drink a glass of water, you are drinking hydrogen and hydroxide ions. Not in a huge quantity, but you are actually drinking ions. So we can write the K for this reaction. If we were to write the K for this reaction, what would it look like? This would be a good time to pause your video, try and write out the K. Now the catch here is you want to only include things that are aqueous or gases, and you don't want to include liquids and solids. So what that means is the denominator is 1. The ions are aqueous, obviously. The water is going to be a liquid, so the water doesn't actually get incorporated into this equation. Now, this is the K specific to the auto-ionization of water. And so we are going to give this K a subscript so that we know it's for a specific reaction. So what subscript do you think would be appropriate in this case? It's going to be a little W. So if you see the KW, what that represents is the law of mass action, the equilibrium constant for the reaction for the auto-ionization of water. Okay, now interestingly enough, at STP, the concentration of hydroxide is going to be equal to the concentration of hydrogen. So notice, if this reaction goes forward, you're going to end up with 2 ions, right? You're going to end up with hydroxide as one of your ions. You're going to end up with hydronium as the other ion. And these 2 ions are always going to happen in a 1-to-1 ratio. If 2 waters react, you get these 2 ions out. There's no other way to cut that cake, right? So the concentration of hydroxide is always going to be equal to the concentration of hydronium. And at STP, there is a specific K. So you can actually go look that up. What's the KW of water at STP? That's a known constant value of K. Now, we don't have to go look it up because we can figure it out, because I'm going to tell you that at STP, the concentration of hydroxide is equal to the concentration of the hydronium ion, and those concentrations are equal to 1.0 times 10 to the negative 7th molar. So automatically you can see that this doesn't happen to an appreciable amount, right? For every, let's see, 1.0 times 10 to the negative 7th mole per 1 liter, right? So if you have 1 liter of water, 1 liter of water, we can imagine that, you're only going to have 1.0 times 10 to the negative 7th mole. 1, 2, 3, 4, 5, 6, 7 moles. That's not very many moles, right? It's a pretty small amount of moles. So you can see that the equilibrium for this reaction highly favors water. Most of the time, the reaction doesn't move forward. Equilibrium is going to lie far right. You're not going to be drinking very many ions, in other words. Okay, so using this information, we can calculate Kw. So go ahead and do that. What would our Kw be? All right, fun fact, friendly reminder, when you are multiplying numbers that are exponents, you can divide up this math in terms of the base number and the exponent. So 1 times 1 would be equal to 1. And then 10 to the negative 7th times 10 to the negative 7th, you're just going to add those exponents. So you get 10 to the negative 14th. So the Kw for the autoionization of water at STP is going to be 1 times 10 to the negative 4th. Again, that's a known constant. That's going to come up for you again and again and again and again. It would be a good number to know, to have memorized. You'll probably memorize it as you do your problems just because you're going to deal with it a whole lot. You're also going to memorize it for a different reason once we get into talking about the pH scale. Just a little preview there. Do you know what the pH scale goes to? Normally, we talk about the pH scale going from 0 to what? Okay, that is related to the Kw, and we'll talk about that in just a couple slides. Before we move on, though, I do want to point out a couple things. First of all, this K, let's think about this, the meaning of this K. Is this a very large K or is this a very small K? And this is an extremely small K, a very, very, very small K. Normally with like weak acids and weak bases, we see K values that are about on the order of like 10 to the negative 3, negative 4, negative 5. Okay, so this is an extremely small K value. So where is this, again, where is this equilibrium going to lie? It's going to lie very, very, very far left, right? It's going to lie on the reactant side. So when this reaction hits equilibrium, when we have a body of water and the waters start colliding, forming ions, the ions start colliding, forming water, we get the rate of reaction equal in both directions. Where is this equilibrium going to lie? It's going to lie with most of our body of water still being water, and not very much of our body of water will exist as ions. We have a very small K, and that's what it's going to support for us. Also, in this case, notice that we have water acting like an acid, and we have water acting like a base, right? We have our hydrogen donor, that would be our acid. We have our hydrogen acceptor, that would be our base. So is water going to be a very strong acid? According to its K value, is water a very strong acid? And because it has such a small K value, you can confidently say that water is not a strong acid. If we compare it to other acids, it's going to lie very low on the scale. In fact, we can go ahead and do that. Let's look at this chart again. So this is some Ka values for some common monoprotic acids. And notice they're all weak acids, right? There's no strong acids on here. Strong acids would be up here and would have K values that are very large, right? Larger than what's listed. So these are common weak acids. Notice you have like HClO2, so that would be chlorous acid. You have HF here, hydrofluoric acid. You have HNO2 here, that'd be nitrous acid. Acetic acid are most commonly used. Weak acid is on here. And notice some of their values. We have at the very top, we have orders of the negative second. HF is to the order of the -4, acetic acid to the order of -5, and even some of these things like ammonium is on here. This one is to the order of -10. We're getting pretty small as far as the K values go. But water as an acid would be even weaker. We would put water on this scale here, 1 × 10 to the -14. And so water actually becomes this dividing line. Notice that we have a dividing line up here between strong acids and weak acids. Well, water becomes a dividing line for us also between weak acids and useless acids, or if that term bothers your tender heart, you can also say very weak acids, right? So these would be the conjugates of strong base, like Na+. Na+ would be a useless acid. It's the conjugate acid to a very strong base, and it's going to be an even weaker acid than water. I don't know what the Ka is for this, or if you can even measure it, but we know it's going to be even smaller than 1 × 10 to the -14. The Ka for Na+. So it'd be some, I don't know, we could make it up. 1 × 10 to the -20, for example, would be a reasonable Ka for the Na+ ion, which can technically act as an electron pair acceptor, because it's positive. So it would be a Lewis acid, right? But it's going to be a very, very weak Lewis acid, weaker than water. What that means is if you have a container of water and you put Na+ into that container, Na+ is not going to react with the water and push it forward in order to create hydrogen ions, right? That would be theoretically if the sodium ion could act like an acid. It would react with water and it would push it forward to somehow create hydrogen ions in the solution. Actually, what it would probably do is just connect with some of those extra electrons that oxygen carries around and kind of form a complex, right? But it's not going to happen. This reaction is not going to happen because water or sodium is a useless acid. And what that says is water will produce more hydrogen ions by reacting with itself than it will with reacting with sodium. Sodium's going to be a non-player in this reaction because it's such a weak acid. It's a useless acid. Okay, so we're starting to connect all these concepts. We have a concept of what a strong acid is. We have a concept of what a weak acid is, concept of what a useless acid is. We have a concept of what K is, what equilibrium is. We're kind of trying to connect all of these concepts together. This would be a great thing for you to pause or revisit in like a day or two and try to outline, try to explain, try to chart, try to draw connections to between all of these concepts. They sound like facts, but they're not just facts to memorize because you have to understand the relationship between all of these things. So trying to put it into a concept map, for example, would be a good idea. Trying to build a Venn diagram where you're comparing a couple things. Those would all be really good ways to interact with your notes after you've taken a lot of these because they're so concept heavy. All right. Coming back to some of these relationships, KW is actually very, very significant when it comes to determining acidic solutions and basic solutions. Remember, the KW is going to be 1 times 10 to the negative 14th at STP. Now, if we are to add things in to this solution, what that does is it messes with our hydrogen and hydroxide concentrations, right? So if we have only water present, then that water is going to split into a 1-to-1 reaction of hydrogen and hydroxide concentrations. They're always going to be equal as long as you just have water present. But once you start putting other things in there, that starts to react with water more so than water reacts with itself, you're going to skew this hydrogen and hydroxide concentration relationship. So we get into these definitions of what is a neutral solution, what is an acidic solution, what is a basic solution, right? Remember that the KW is a relationship that is always true as long as you're at STP, right? KW is going to be 1 times 10 to the negative 14 no matter what your equilibrium positions of your two ions are, right? Equilibrium positions can go up or down. The equilibrium constant stays the same, and that's true in this case also. Okay, so let's start with a solution where we have only water present. If we have a solution where we have only water present, we know the hydrogen or the hydronium ion concentration is going to be equal to the hydroxide concentration, right? These two are going to be equal. That's what neutral means. So before we go any farther, let's just pause here and reflect on the meaning of neutral again, right? A lot of times, what people assume is that in a neutral solution, you have no ions present, and that's not true. That's a misunderstanding of what neutral means. Just like in an ionic compound, if you're thinking about an ionic compound that contains the sodium ion and the chloride ion, right? In an ionic compound, it's not that you have no charges present, it's that you have equal amounts of your positive and your negative. If we're going to combine the sodium ion with like the sulfide ion, right? We're going to need 2 sodium ions, Na2S, in order to balance out this compound because we want our positives to be equal to our negatives, right? It's the same thing in acidic and basic solutions. Neutral, if you're chemically neutral, it doesn't mean that you have no hydroxides and hydroniums present. It means that you have equal amounts of hydroxides and hydroniums present. So this is kind of an extreme concept, right? You can actually take solutions that are very dangerous, like let's say 12 molar hydrochloric acid, which would give you 12 moles per liter of your hydronium ion. If you were to drink that, you would die. It's a very dangerous solution, right? If you combine it with 12 molar sodium hydroxide solution, so in that solution you have 12 moles per liter of your hydroxide ion, right? If you were to drink that solution, you would die. It's a very dangerous solution. You just spill it on your skin and it hurts, right? Now, if we were to combine these two, we would get a solution where our concentration of hydronium is equal to our concentration of hydroxide. And that, my friends, is a neutral solution. You combine these two things that are very dangerous, you combine them in one solution, you still have lots of ions present, but they're present in equal amounts. You have a neutral solution that is no longer dangerous. Theoretically, you can drink that. I think there is a crazy professor out there somewhere who does this as a demo for his students every year. Ultimately, he's just drinking salt water. But he starts with very dangerous solutions, mixes them in perfect ratios, drinks it, and he is fine, maybe a little high in salt, but otherwise totally fine every year. Now, would I do this? No, I would not, because I do not trust my measuring devices or abilities or my solutions as much as this guy does. He must have excellent dilution technique. So, life goals, right? Okay. Anyway, moving on. So neutral means you just have the same amount of hydronium and hydroxide ions present. So what does acidic mean? If you have an acidic solution, you're going to have more hydronium ions than hydroxide ions. Again, they're going to have to multiply together to still equal the same kW as long as you are at STP. So mathematically, if your hydronium ions go up and you want your constant to remain the same, what do hydroxide ions have to do? They have to go down, right? So your equilibrium positions can change, your constant will remain the same. And then same thing with a basic solution. In a basic solution, you're going to have more hydronium than hydroxide. Same idea. If hydroxide concentrations go up, what do hydronium concentrations have to do? They have to go down so that your equilibrium constant stays the same. Remember, the K is not going to change unless you change that temperature. In all cases, those two quantities are going to multiply together to equal 1 times 10 to the negative 14th as long as you are at STP. Okay, so the next concept I want to talk about is the pH scale. So when you talk about acids and bases, people automatically start throwing around this idea of pH, right? So let's talk about what the pH scale and what it actually does and doesn't communicate. The pH scale can be really misleading. So especially in society, people have this misunderstanding of what the pH scale is, right? They think 7 is neutral. And we already kind of talked about how neutral means there's the same amount of H plus and OH minus ions, right? Not that ions are missing, but that they're present in equal amounts. Another thing that people will automatically assume about the pH scale is that if something is lower on the pH scale, that means it's a stronger acid. Or if something is higher on the pH scale, it means it's a stronger base. And that's not true either. Yes, the pH scale does reflect strength of acid, but it also reflects concentration. And so we can have something that's a weak acid like lemon juice, right? Citric acid is the acid that's in lemon juice. Citric acid is not one of our 7 strong acids. So citric acid is a weak acid, right? We eat it. You can squeeze out a lemon and drink the juice and you're going to be just fine. In fact, it's probably healthy for you, right? But if you were to squeeze out that lemon juice and test it with a pH meter, you're going to get a really low pH. You're going to get a pH that is probably at the bottom of the scale, like a pH of 1 or a pH of 0, or maybe even negative, like a pH of -1. And the pH being so low is not necessarily a reflection of the strength of the acid. So this pH scale is complicated, and we want to talk about it a little bit and kind of break it down so we really understand what is actually being communicated when pH gets communicated. So like we talked about before, the pH scale is a range, and it's a range from about 0 to about 14. And then in the middle of the scale, therefore, would be 7. Now, the pH scale doesn't actually start and stop there. The pH scale can continue on below 0, and it can continue on above 14 as well. That's just kind of like the parameters that we start to use. pH is a logarithmic scale. So this is the other thing that you need to understand about pH. If we're comparing a pH of 7 to a pH of 8, we're talking about a difference times 10, right? But in a pH of 8 to a pH of 9 would be another difference in powers of about 10. But if you are talking about a pH difference of 7 to 9, you're not talking about a pH difference times 20. It's not double. It's multiplying exponents, right? It's a pH difference of 100, right? And so these notches on the pH scale get multiplied by a power of 10 every step you take. And so it's a logarithmic scale. It's not a linear scale, and that's going to change our understanding of concentrations when we're trying to compare two different pHs, right? Now, pH is a direct value of the concentration of our hydrogen ion, or that would be our shorthand, right? Actually, we're talking about our hydronium ion. So it is reflecting a measurement of the concentration of a hydronium ion. Now notice it's a negative log, so the higher our concentration of hydronium gets, the lower we're going to be on the scale. So acids are going to be on this side, very low pH, very high concentration of hydronium. Bases will be on the other side, which have a high pH and a low concentration of the hydronium ion. As far as sig figs go, whatever the sig figs were in your original number that you plugged in as the concentration, that's the number of sig figs you keep on the pH. So for example, if I have like 3.12 times 10 to the negative second concentration, and that is the concentration of my H plus, whatever the pH is that I get out, I'm going to keep that pH to 3 significant figures. So when you're looking at sig figs, that's about as deep as we're going to go into keeping sig figs with logarithms. Whatever you had in the beginning, just keep it in the end. Okay, there are other log scales. So notice this is pH, right? Well, we can also have a pOH. So a pOH scale would be the negative log of the concentration of hydroxide ion, right? We can also have a pK scale. A pK scale would be the negative log of whatever our K is, our KW, our KA, our KB, our KEQ, right? We can take whatever our K is, plug it in, and get a pK. So when we're talking about these like P scales, you're just taking the negative log of whatever you're talking about. Now, these things become very useful to us. Okay, so for example, we can calculate the pH and the pOH for a specific solution if we know the concentration of hydroxide or hydronium, right? So if I have the concentration of hydroxide here, I can plug that in to negative log of my concentration, and I'm going to get out a pOH, right? So I'll do that. real fast. Okay. All right, so I'm going to get a 3 equals my POH. Okay, so a couple things to notice before we go any farther here. Notice it does ask us to calculate POH and pH. Is you can approximate what the pH is going to be based on your exponent, right? So if it's a 10 to the 3, your POH is going to be around 3. If it's a 10 to the 6, your POH is going to be around 6. Now, the base unit, the integer there, is going to mess with that a little bit. If the integer there is 1, then your pH or POH is going to be exactly what your exponent is going to be. If your integer that's attached to your exponent is something else, it will mess with your pH or POH, but you're still going to be close. So this is one of the keys when you're doing multiple choice questions on the AP exam, and they ask you to do some log scales. You know that your answer is going to come out really close to whatever your exponent is, right? Okay, so now if we have the POH, how do we get to pH? Well, the only thing we have right now that relates them is Kw. Remember, Kw is the concentration of H plus times OH minus. We know what Kw is because we're dealing with a temperature of 25 times 10 to the 25 degrees Celsius. So my Kw is going to be 1 times 10 to the negative 14. We're looking for the H plus concentration. The hydroxide concentration is 1 times 10 to the negative third. Again, when you're dividing by an exponent, notice that our base numbers are 1, which is very nice of them. Again, you can go 1 divided by 1, which is going to be 1. And then you can go, if you have times 10 to the negative 14 divided by times 10 to the negative 3, you're just going to subtract off your exponents, right? So that's going to be times 10 to the negative 11th equals your concentration of H plus. So now we can take that, plug it into our pH, equals negative log of 1 times 10 to the negative 11. And again, because our base unit is 1, our pH is going to come out to be 11. So our pH is 11. Our POH is 3 for A. So go ahead and try that on B and let me know what you get. Okay, so notice we got a POH of 0, right? So now we have to figure out what our PO or our pH is. So pH is going to be 14, POH is going to be 0 for B. Is that what you got too? Okay, last thing, notice that we do have this relationship of Kw that we just used on the last page. That one's going to be one of your equations you can kind of manipulate to get out what you want to get out. But if we take the negative log of both of them, remember the negative log of Kw is just going to be pKw. The negative log of H plus is going to be pH, and the negative log of OH minus is going to be POH. And whenever you take the negative log of two things that are multiplied, you're going to end up adding them. So we get this second relationship here, which is pKw equals pH plus POH. So now we can actually calculate what this is for the pKw at 25 degrees Celsius, at STP, right? 1 times 10 to the negative 14th. We've already seen the negative log of 1 times 10 to the negative 14th is 14. And so here is a third relationship we have between them. Now, all of these relationships are derived from the same relationship, so you can just continue using this first one. But these other two kind of give you a shortcut. So at STP, pH and POH together equal 14, and we saw that on the other page when pH was, 3 maybe, and POH was 11. Oh, maybe it was the opposite. I think POH was 3 and pH was 11. Either way, they're going to add up to 14. Similarly, if POH is 0 and pH is 14, they're going to add up to 14, right? So that's a really convenient relationship. We can go back to that last slide, and if we had this other relationship with the P's, it would have saved us some time. We could have, let's go, buddy. Once we figured out that this POH was equal to 3, then we just take 14 minus 3 to get 11, and that's going to equal our pH. So again, you don't need that relationship of pKW equals pH plus POH, but it's going to be a time saver for you in certain circumstances when you're trying to decide between the two equations what's going to be faster. It helps to have them both in your pocket. Okay, so we'll work with this stuff together in class. Let me know what questions you have, and I will see you in class.